So for the sake of time, yes, Dawn is here. Dawn and I will be facilitating this session. My name is Gaye Ceyhan. I'm at Boğaziçi University in Science Education program. Dawn, do you want to introduce yourself?
Yes, Don DeLand. I'm in Albuquerque, New Mexico, in the U.S. Spent a career in math education, and currently I'm a doctoral student in educational leadership. So,
Perfect. Welcome everyone again to the higher education breakout room. We will be guiding our session today with Dan. Before we begin, a few quick housekeeping suggestions and items that we need to mention. Please make sure your full name is displayed in your Zoom window. I can see that everyone has their names. Perfect. We are recording this session, so please be aware of that. And in this session, we have one presentation followed by an extended discussion and answer period. So there will be plenty of time for discussion, hopefully. Please feel free to take your notes in the chat as we go, or you can raise your hand at the end of the presentation. Our presenters are Alexandra Tepla from the University of Vienna in Austria, together with Tom Bielik from Radboud University in Netherlands. They will present their work on developing and evaluating a task on ocean acidification. Alexandra and Tom, please introduce yourselves, and the floor is yours.
Yeah, I think I can start. I will also introduce Alex. So, hi everyone. Thank you for joining, and thank you for the invitation to have the opportunity to present here today. Yeah, as was said, I'm from the Institute for Science Education at the Radboud University in the Netherlands, and I will. My job here today is the easy one. I will just present the student that I'm co-supervising, Alex, and we are supervising her. I'm supervising her together with Anya Lembens, who is also here, I see. So I will just say that well, my background is research mostly on topic of computational modeling and also with system thinking, and I'm also part of the team that developed the Sage Modeler modeling tool in Michigan State University quite a few years ago. And yeah, I'm happy to be part of this symposium for the second year in a row. So the one that is the focus of this presentation is Alex, and she's our PhD student from the University of Vienna. I will just say that she is a very promising early career researcher in the field of system thinking and coming from chemistry education, so mostly discipline based, and she will share her initial findings and the project that she's been working on in the last year. This is only her first year still of her PhD, so still early findings, but she already did quite a lot, not just on her research specifically, but also for the community of the system thinking, system dynamics, mostly in the European context. And she organized in the latest ESERA conference a network event that kind of jump-started the community for all of us. Also, Gaia is involved in that for working together, thinking together, networking on these topics. And this group has been going since then, since last summer. And also she is behind a new SIG, a new special interest group that we are organizing about system thinking and modeling for ESERA. So some of you are already involved with that, and those who are not are welcome to join. We will hopefully get it started in the next few months. We just need to finalize a few things. So yeah, Alex is very much involved in all of that. Yeah, so for the rest of this half an hour, she will be presenting her research, and also we will have some time for discussion after that. So Alex, the floor is yours.
Thanks, Tom. Thank you very much for setting the expectations quite high. As Tom said, I will present my research project today, or at least first insights from my research project. And for that reason, I will share my screen. I think it should be working now.
Yes.
Okay. Great. So, okay, one moment. I just need to set up because I don't see my screen. That's unfortunate. Okay. All right. Now, as Tom said, my name is Alexandra Tepla. I'm from University of Vienna. And today I'm presenting first insights from the evaluation of a task on ocean acidification to foster or to analyze system thinking in secondary students, which is part of my PhD research. Let me briefly guide you through the next 15 to probably 20 minutes of this talk. I'll start with some contextual background on why this topic is relevant. Then I'll move on to theoretical foundations of systems thinking and ocean acidification. And after that, I'll present the task, how we evaluated it, followed by some preliminary results, and of course, a short discussion of our results. So many global challenges, such as climate change, can be understood from the perspective of complexity theory as complex systems, rather than linear cause-effect relationships. And understanding these systems, navigating within them, and ultimately acting responsibly is therefore one of the key goals of science education. However, if you look at the more traditional science teaching, it becomes clear that understanding isolated subject knowledge is no longer sufficient, but what is needed is something more, a more connected way of thinking, and this is where systems thinking in science education comes in. The relevance of system thinking is, for example, also part of as a part of scientific literacy is also reflected in current educational frameworks. For example, here in the PISA 2025 framework, for instance, it's emphasized that 15-year-olds, old students should be able to use system thinking to understand and respond to complex global challenges. And also, of course, as part of education for sustainable development, system thinking is considered as a key competency for addressing multiple SDGs. But what exactly is system thinking, and what framework do we draw in our research? We interpret system thinking as the ability to understand and interpret complex systems, to recognize interconnections, to integrate the elements into a coherent overall picture, and of course also analyzing system behavior and identifying patterns and emergent phenomena. Now, I don't know if you teach or ever taught 15-year-olds, but I do, and I think this is quite a lot to ask from 15-year-olds. But the good news is we know already from current research that system thinking can be developed through carefully designed instruction. And at the same time, system thinking does not happen in a vacuum. It always needs some kind of meaningful context. And in our project, this context is ocean acidification. So to give you a little bit of background knowledge, I don't know if everyone here is accustomed to ocean acidification. Let's take a look at this diagram. This data comes from the Mauna Loa Observatory, and it shows a very clear trend. Carbon dioxide levels in the atmosphere are steadily increasing, not only there, of course, but worldwide. Why is that a problem? Well, the carbon dioxide in the atmosphere is part of the global carbon cycle. It does not remain in the atmosphere alone. Instead, it enters the ocean through different pathways. For example, as the biological pump, which is here depicted as the zooplankton and the large phytoplankton, but also through, for example, upwelling and different physical pathways. And this has different effects, where chemistry also comes to play. And due to the increased amount of carbon dioxide entering the ocean, more carbon dioxide reacts with water to first form carbonic acid, and after a few other steps, ultimately leads to the formation of hydrogen carbonate and hydronium ions. And these hydronium ions are crucial because they lower the pH value. In other words, they make the ocean more acidic. So in this figure, you can see that over the last, let's say, 50 years, the pH value of the ocean has decreased by about 0.1. At first glance, this might not seem like a large change. However, we have to keep in mind that the pH scale is logarithmic. So this means that the concentration of hydronium ions at a Aloha research station has increased by 26%, which is almost a third in less than 50 years. And as you can imagine, such a drastic change is not unproblematic for marine ecosystems. One major effect of this ocean acidification is the reduction in calcification rates, especially in organisms like corals or other calcifiers. At the same time, existing calcium carbonate structures can start to dissolve. And this can in turn lead to cascading effects on biodiversity and fisheries, for example. And these ecological changes also in turn have economic and social consequences, for example, for food security. In addition, due to ocean acidification, we may lose important ecosystem services such as coastal protection, which is often provided by coral reefs, as well as, of course, benefits related to tourism and cultural value. So as you can see, ocean acidification is a highly complex issue with multiple causes, effects, and different actors involved. And that's why we chose this context to develop a learning task with the goal of letting students, first of all, demonstrate their system thinking skills and later on maybe improve their system thinking. To make this complexity a little bit more manageable, we focused on one concrete phenomenon of ocean acidification, which is the decrease in the number of corals. As a first step, we mapped the system, the underlying system in a co-construction process with another PhD student from my research group. And then we developed before and after pictures as a central element for our task, which I will explain in more detail on this in the next slides. So during the task, our students go through several phases, and each phase is targeting different system thinking skills. At the beginning, the focus is on rather basic skills, such as describing the elements in the initial picture. Here you can see the fictional landscape of the before situation, together with some students' example responses. For example, they identified the components fish, factories, trees, fishing boat, and so on. So this is a quite easy task. Students are then asked to identify changes between the before picture and the after situation, which is depicted here. Also here you can see that the answers of what's changed in these two pictures are quite analytical. They identified fewer trees, fewer fish, more factories, fewer corals. Building on this, students are asked to develop explanations for the observed coral decrease. And here they came up with a lot of different ideas. For example, water pollution from factories, or trawl nets from fisheries, or the increase in temperature due to the greenhouse effect. The students were then asked to visualize the explanations in a so-called causal map. Here you can see an example for such a map. And this is a quite difficult task. To support this process and to ensure that their explanations are not limited by lack of content knowledge, students received input on the submicroscopic aspects of ocean acidification, so the mechanistic aspects, and they also were provided with various scaffolds. For example, here you can see magnifying glasses, which are showing the chemical reactions which leads to the decrease in the number of corals. And of course, they also were provided with other scaffolds, for example, the definition of a pH and the components that were part of these reactions. After this input phase, students had the opportunity to revise and improve their causal maps. And as you can see here, the the map from earlier is now quite developed and it became more detailed. In the final two tasks, which are more modeling tasks, they zoomed out again. They were asked to make a prediction, for example, how the system might look in 50 years if a new technology is introduced, and also to reflect on their own role within its system, which is quite interesting for Austria since we're a landlocked country, we don't have an ocean. Right, so much for the task itself. We have already conducted a first pilot study, and I would now like to briefly present our approach. We carried out 5 task-based interviews with a total of 10 upper secondary students in Vienna, Austria. And the data we collected included the causal maps, both before and after the instructional input, as well as audio recordings of the interviews. The maps were first digitalized and then scored. I will explain this in more detail on the next slide. And afterwards translated for international purposes, such as this symposium. The interviews were transcribed, and we conducted the first round of topic modeling to derive deductive categories for a subsequent qualitative content analysis. But this is still a work in progress, so we're still working on that. We have analyzed the maps along 6 different dimensions. First of all, the descriptives capture basic structural features, such as the number of nodes or of connections of junctions. Second, we have the dimension of scientific accuracy, where we look at how scientifically appropriate the content of the map is, including what concepts, for example, are included in the map or are missing. And we did this based on a reference map, which you can see here on the left side. The third dimension is coherence. And here we refer to how well the maps align with what participants actually said in the interviews. For example, whether the direction of arrows matches their explanation. Sometimes they have difficulties in this. The fourth dimension we called granularity. And here we focus on the level of representation in the map. Here we're drawing on Johnston's levels. I don't know if you're familiar with that. There are 3 different levels: submicroscopic, macroscopic, and symbolic level. And we looked at how these levels were used and how well they were connected. The 5th dimension we used was complexity, and it's based on the Solo taxonomy. And here we look at how structured and interconnected the maps are. And finally, the causality dimension, which is based on Tina Grotza's framework, examines what type of causal reasoning is used in the argumentation process. Right, so to illustrate how this scoring works in practice, I'll show you an example map along with its analysis based on these 6 dimensions. Here you can see an example of one of these causal maps. This one was created before the instructional input. So for this example, the map includes 13 elements and 8 connections, all of which are causal. In terms of scientific accuracy, the students correctly identified increased water temperatures as a key driver for coral bleaching, but the aspects for ocean acidification are missing. So the system is not explained completely. Regarding the coherence of the map, we now see that causal relationships are indicated with arrows, but sometimes the logical order remains unclear. For example, if you look at the element mangrove forest deforestation, which is connected to less CO2 is bound, this argumentation does not really make sense from the map. But if we do an overlay with the interviews, we know what the students wanted to say. But that's what we meant with coherence of map and interview. So the argument doesn't make sense in the map, but it does in the interview. For granularity, the map mainly operates on a microscopic level. We have some submicroscopic elements included, for example, less CO2 is bound, but these levels are rare and weakly connected. And in terms of complexity, we can see that the structure is 2 chains which merge at the end. So we're starting from aircrafts, refineries, etc., and mangrove forest deforestation, and we end in biodiversity declines and fish habitats destroyed. In terms, finally, in the sixth dimension, causality, the causality is mostly linear. We have a very one-directional reasoning, and it's mostly domino reasoning. So A leads to B, leads to C, leads to D. However, we have a good example for a relational reasoning, which is emissions increased leads to anthropogenic greenhouse effect, and less CO2 is bound. So we have two different factors that impact our next factor, our next element, anthropogenic greenhouse effect. This is an example for relational reasoning. Okay, so what did we learn from this pilot study so far? First of all, we made some design-related adjustments, of course, to better focus on the task and also to improve the wording in some parts. But we can also see some interesting patterns in the data. Identifying the components and describing the changes seems to be relatively easy for students, which is in line with other system thinking frameworks where these skills are considered more basic skills or novice level skills. We also observed that after the instructional input, students used more levels of explanation. So in particular, they more frequently included the submicroscopic level, which then in turn also led to more scientifically appropriate explanations. However, we found that there was little change in terms of complexity and causality. The map still showed few interconnections, almost no feedback loops, and students' reasoning remained largely linear. So this aligns with findings from previous research, which shows that even with complex systems, learners tend to rely on linear cause-effect explanations, and they rarely consider feedback mechanisms unless explicitly prompted, which we did not do in this task. Interestingly, more advanced skills, here we have more advanced skills, such as making predictions and reflecting one's own role in the system, were handled relatively well. Students referred to different subsystems and adopted multiple perspectives. So they showed some signs of system thinking in the easier and the higher level phases, but these aspects were not reflected in the causal map, so in the explanatory part of the task. So this leads us to an important follow-up question that we would like to explore further, which is, are the observed patterns of using system thinking a result of our task design? Maybe the time on task, they had approximately 45, 50 minutes, or maybe disciplinary teaching traditions, something completely different. As Peter Sengi said in the keynote, at least the Austrian educational system and the traditional chemistry education in Austria is not set up to teach chemical phenomena as systematic phenomena. So maybe we can't even expect students to explain chemistry phenomena in a systemic way when they're never taught to do things like this. So to address these issues or to address this question, our next steps include to take a deeper look into their students' argumentation process with our topic modeling approach combined with qualitative content analysis, and then, of course, by further revising the task and trying to zoom out in the explanatory part as well. So as you can see, there's still a lot to do. We're at an early stage of the project, and that's why I'm very much looking forward to your questions and the discussion, and I'd like to thank you for your attention.
Thank you, Alex. It was a great presentation, and I'm looking forward to see the final results. These are the preliminary results, and that looks promising. So we have 5 minutes for the question parts. Are there any questions? Yes, I see.
Hi, I'm Jensen from Singapore. Thanks for sharing your research. I have actually two questions. I think you might have said somewhat. I'm just wondering whether in the student descriptions, right, do they describe it with a feedback loop in mind or just purely linear? So that's the first question. And the second one is I wonder whether the students get confused when they use multiple level variables, where maybe variables could be individual, but it goes to societal and they get confused. So I wonder, is there such confusion? So these are two questions there. Yeah.
So for the first question, if I understand the question correctly, you're asking whether the students showed also feedback mechanisms in their explanations, right?
Yeah. So did they say A influence B, influence C, and influence D?
No, most of the reasoning was actually quite linear. Even after the input phase, it didn't really change. They showed the system thinking and the feedbacks, they explained it in other parts of the task. For example, in the prediction part or in the reflection of your own role. That's where they showed also feedback mechanisms to some extent. But in the explanation part, they really stuck to the linear reasoning. And did this answer your question?
Yes. So
Okay.
what is telling me that they are not thinking in system?
Sorry?
You're sharing with me that they are not thinking in system, am I right? Based on the data, at least.
No, they are showing some types of or some skills of system thinking, especially in the lower level skills like identifying components and connections, and also in the higher level skills like predictions and your own role in the system. But they're having difficulties using system thinking in explaining a chemical phenomenon. That's what we can see here.
Thank you.
Right. And your second question, I don't know I think I forgot your second question. Sorry.
So I'm just saying that does a student get confused when they identify
right.
multiple level variables? Yeah.
Yes, they did get confused. Well, partly. First of all, they mainly used the macroscopic level, so phenomena at the before picture, before the intervention, the instructional part. And then afterwards, they used the mechanisms, the submicroscopic mechanisms, but they improved in connecting it. At first, they didn't really know how the CO2 from the atmosphere can do something to the corals and how it dissolves like in water, what it has to do with it. But after some time, they got used to explaining the phenomenon with the submicroscopic mechanism, which is one of the goals of chemistry education, where we're aiming to teach students to think about the phenomena as particles, as emergent phenomena of particles. Right. Thanks.
Thank you, Alex. We have 1 minute for quick question from Kim and quick response from Alex.
Yes, I was very excited to hear about your project. My PhD was in oceanography, so this was amazing. Late in my career, I did some research on how people think and learn about feedback loops, and we made a scoring rubric for causal loop diagrams. And we found results similar to yours, that students' individual A arrow B links were sometimes not related to reality in any kind of plausible way. So I can send you the link to the to that piece of research, so at least you have something else to cite to show that that was found someplace else. But my question to you is, do you have a hypothesis about why students draw what they understand to be a causal link with the thing at the upstream end not connecting to the thing at the downstream end in any way that relates to a real Earth process?
I do. First of all, I would be very happy if you could send me your paper. Thanks. And for your question, I do have a hypothesis. First of all, they really didn't get a lot of instruction on creating causal loops. So that was kind of new for them. And maybe they weren't familiar with creating a causal map. This is one hypothesis. And the other one is, again, how we're teaching chemistry in Austria and probably also in other countries, is that we're trying to explain phenomena with particles, but we're never trying to explain them as part of a bigger system. So we're not trying to show that it's not common to explain a phenomenon as an emergent phenomenon. And even if we explain basic structural relationships in chemistry, then it's on a very analytical and linear level. This particle movement leads to this phenomenon.
Yeah.
So we can expect them really to explain it differently.
Yeah,
probably.
With our instruction, students did draw things that looked like causal loop diagrams. They did go in a circle. But when you zoomed in and looked at the A arrow B, there's no logic. There's nothing in either data or theory that stands behind why this A is connected to this B with an arrow that goes in this direction. We did develop a precursor activity that helps people get past that problem, which I can send you as well. So you're doing great work. So best of luck in your
Thank you so much. Thank you.
Okay, thank you. It was a great presentation and great discussion. Thank you, Alex and Tom, for this contribution. Now we are going to move into the next session. I'm going to stop recording first and then record again